Chart. Denver International Airport sits 1 mile above sea level, receives an average of 60 inches of snow each winter, and operates 24 hours a day without closing its runways. Most major airports shut down after 12 inches. Denver keeps moving through twice that amount while handling 77 million passengers a year. The question isn't whether the airport can survive a blizzard. It's how the infrastructure was designed to make closure physically unnecessary. Licensed media. Aerial view of Denver International Airport during active snowfall. Runways visible. Aircraft taxiing. When Denver International opened in 1995, it replaced Stapleton International Airport, which had become operationally landlocked and dangerously prone to weather delays. The new airport was built on 53 square miles of prairie 25 miles northeast of downtown Denver, making it the largest airport by land area in North America. That footprint wasn't chosen for future expansion alone. It was engineered to handle the meteorological reality of the Front Range urban corridor, where winter storms drop heavy snow, high winds reach 50 miles per hour, and temperature swings of 40 degrees in a single day create ice, slush, and freeze-thaw cycles that crack pavement and disable equipment. Diagram: map showing Denver International Airport location relative to downtown Denver and Front Range geography. The central constraint was this: Denver needed an airport that could maintain operations during conditions that would ground other hubs. The Federal Aviation Administration categorizes airport snow removal performance by how quickly runways return to operational status after precipitation stops. Denver's design goal was different. The airport needed to keep at least one runway open during active snowfall, not just recover after the storm passed. This requirement shaped every major infrastructure decision, from the number of runways to the power capacity of the central utility plant. AI reconstruction. Illustrative view of airport runway configuration from above, showing 6 parallel runways oriented north-south. The solution began with runway orientation and quantity. Denver International has 6 runways, all aligned north to south. That alignment follows the prevailing wind direction along the Front Range, reducing crosswind landings during storms. 5 of the 6 runways are 12,000 feet long, allowing aircraft to land and take off with longer distances when snow reduces braking friction. The 6th runway stretches 16,000 feet, the longest public-use runway in the United States, designed to handle fully loaded international departures even when surface conditions degrade performance. Data visualization. Runway layout schematic, showing 6 parallel runways with length measurements and spacing, but runway length doesn't clear snow. The airport maintains a fleet of over 300 pieces of snow removal equipment, including high-speed broom trucks, blowers, loaders, and chemical applicators. A single runway sweep during active snowfall requires coordination among multiple vehicle types, moving in formation at speeds up to 40 miles per hour. The fleet is divided into teams, each assigned to a specific runway or taxiway section. When snowfall begins, teams activate in rotation, clearing one runway while aircraft continue using the others. This rotating closure strategy means passengers experience delays measured in minutes rather than cancellations measured in days. Licensed media. Snow removal equipment in coordinated formation on airport runway, showing scale of machinery. The pavement itself was engineered with embedded heating elements beneath critical areas, including portions of taxiways and gate aprons where aircraft must maneuver at low speeds. Heated pavement prevents ice bonding, eliminating the need for mechanical scraping that damages asphalt and delays aircraft movement. The system draws power from the airport's central utility plant, which was sized during construction to support continuous heating loads during multi-day storm events. During the design phase, engineers calculated heat output requirements based on the worst-case scenario: 3 consecutive days of snowfall with overnight temperatures below 0 Fahrenheit. Diagram: cross-section illustration of heated pavement system showing embedded elements and surface layers. Chemical treatment posed a separate engineering problem. Potassium acetate, the airport's primary desing fluid, works at lower temperatures than traditional sodium chloride, but costs significantly more and requires precise application rates. Overuse contaminates stormwater runoff, underuse leaves ice on critical surfaces. Denver developed a computerized application system that adjusts fluid concentration and coverage based on real-time pavement temperature, precipitation rate, and traffic density. The system reduced chemical use by 30% while improving surface conditions. Sensors embedded in the pavement transmit temperature data every 30 seconds, allowing operators to target only the sections that need treatment, rather than coating entire runways uniformly. Data visualization. Chart showing chemical application rates correlated with temperature and precipitation intensity. Weather forecasting determines when snow removal operations begin. Denver's meteorology team monitors conditions using ground-based sensors, Doppler radar, and direct communication with the National Weather Service office in Boulder. Snow operations typically activate when forecasts predict accumulation rates exceeding 1 inch per hour or wind speeds above 30 miles per hour. At that threshold, equipment crews report to staging areas. Aircraft desing pads activate heated fluid systems, and gate operations extend turnaround times to accommodate slower ground movement. The lead time between forecast activation and actual precipitation arrival averages 90 minutes, giving crews time to position equipment and brief coordination protocols before the first flakes fall. AI reconstruction. Illustrative view of airport operations center with weather monitoring displays and coordination systems. The cost of maintaining this infrastructure is measurable. Denver International's annual snow removal budget exceeds $20 million, covering equipment maintenance, fuel, chemical supplies, and staff overtime during extended storm events. A single major blizzard can consume $2 million in direct operational costs. That expense buys operational continuity. When other major airports close during winter storms, Denver becomes a critical diversion point for flights that cannot land at their original destinations, generating additional landing fees and passenger services revenue that partially offsets snow removal costs. During a typical winter season, diverted flights contribute an estimated $5 million in unplanned revenue. Licensed media. Aircraft landing at Denver International during snow conditions, showing operational runway. The system has limitations. Wind speeds above 50 miles per hour force ground operations to halt, regardless of snow depth, because jet blast and crosswinds make aircraft maneuvering unsafe. Visibility below 1/4 mile triggers instrument-only approaches, reducing arrival rates even when runways remain clear. Freezing rain creates surface ice faster than heating systems can melt it, occasionally requiring temporary runway closures until mechanical removal is complete. Denver's infrastructure minimizes weather-related shutdowns but does not eliminate them. The airport's operational target is maintaining at least 2 runways during 95% of winter storm hours, a threshold it has consistently met since 2000. Public domain. Federal Aviation Administration weather minimums documentation showing visibility and wind speed operational limits. Since opening, Denver International has closed all runways simultaneously only a handful of times, each during blizzards that produce snowfall rates exceeding 4 inches per hour, combined with wind gusts over 60 miles per hour. During a March 2003 storm that dropped 31 inches in 24 hours, the airport remained partially operational, closing individual runways in rotation for clearing while maintaining at least 2 runways open throughout the event. Stapleton, the airport Denver replaced, would have closed entirely under the same conditions. The contrast illustrates the return on infrastructure investment. Stapleton averaged 12 full closures per winter season during its final decade of operation, while Denver International averages fewer than 1. Licensed media. Historical footage or images comparing Stapleton Airport during snow events with Denver International operations. The engineering lesson is specific. Runway quantity, orientation, length, heated infrastructure, chemical systems, equipment fleets, and meteorological coordination are not independent features. They form an integrated system where each component compensates for the limitations of the others. Heated pavement reduces chemical dependence. Multiple runways allow continuous operations during clearing. Real-time weather data determines when and where to deploy resources before conditions become unmanageable. Denver moves 77 million passengers through blizzards because the airport was designed as a snow removal system that happens to include runways, not runways with snow removal added afterward. Data visualization. System integration diagram showing interconnections between runway design, heating systems, equipment deployment, and weather monitoring. The consequence extends beyond Denver. Every airport built in snow-prone regions since 1995 has adopted elements of Denver's approach: increased runway redundancy, heated pavement in high-traffic zones, computerized chemical application, and expanded equipment fleets. The design proves that operational resilience in extreme conditions requires upfront infrastructure investment calibrated to the specific meteorological threat, not reactive spending after each closure. Denver International remains the reference case for airports that must function when weather becomes the primary engineering constraint. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.